Here's another definition, and let R be a ring with identity 1. And we say R has finite characteristic. Finite characteristic if there exists an integer, a natural number, such that 0 is equal to 1 plus 1 plus and so on. If we add 1 n times, that is equal to 0, then we say R has finite characteristic. And if there are no such n, then we say, otherwise, R has infinite or 0 characteristic. Okay, so it may sound strange, infinite or 0 characteristic, but so since such an n doesn't exist, so only 0 times 0 ones equal to 0, so it makes sense. So, and even if you have any number of ones, it's not equal to 0, so it's again infinite. So yeah, so that's the definition. And for example, the set of integers has infinite characteristic or 0 characteristic. And Zn for any natural number, then it has finite characteristic. Now, here's a simple lemma involving the notion of characteristic. Let R be a ring with the identity element 1. And suppose it is of finite characteristic. Such that n1 is equal to 0. So if we add 1 n times, then that is equal to 0. Okay, then for all elements A, every element A of R, we have NA equal to 0. The proof of this is very simple. NA is equal to A plus and so on. So we add A n times. And I mean, that's almost the definition of what NA means. But each A is equal to 1 times A. Right, because by definition, 1 times A is equal to A. And using the distributive law, we have 1 plus 1 plus 1 times A. And of course, there are n ones here inside the parentheses. And that is equal to n1A. But since we are assuming n1 is equal to 0, this is 0a, which is equal to 0. And we are done. Now here's a theorem. Let D be an integral domain with identity 1 and of finite characteristic. Okay, then there exists a prime unique prime, so let's say unique prime, such that P1 is equal to 0. So let's prove this. So by assumption, there is some integer, a natural number, such that n times 1 is equal to 0. And let P be the least of such integers. Okay, so this says there are some integers such that this holds, but so such integers may be many of them. There may be many of them. So let P be the least of such integers. Okay, we claim that this P is a prime. So to prove this, we prove by contradiction. Okay, so suppose P is not prime, a prime. So this means we can factorize P. Then P is equal to P1 times P2, where P1 and P2 are between 1 and P. Okay, of course these are integers. Okay, and so let's see, P1 times 1 times P2 times 1 is equal to 1 plus 1 plus and so on plus 1. So there are P1 ones here, and 1 plus 1 plus and so on, and there are P2 ones here. So by applying the distributive law, this will be 1 plus 1 plus and so on, and there will be P1 times P2 terms, right? So this is equal to P1, P2, 1. Okay, but by assumption, P1 times P2 is P. So this is equal to P1. This is equal to 0. But now, we are assuming that D is an integral domain. So since D is an integral domain, there are no proper divisors of 0. Okay, so that means, so if this product is equal to 0, that means either P1, 1 is equal to 0, or P2, 1 is equal to 0. But either way, this is a contradiction because we assumed that P is the least integer such that P times 1 is equal to 0. But here we are having P1 times 1 is equal to 1, or P2 times 1 is equal to 1. And P1 and P2 are less than P. So this is a contradiction. Therefore, P is a prime and is unique, because that's the least such integer that P times 1 is equal to 0. So this is the least, P is the least such integer. This holds. Therefore, it's unique. And we are done. And based on this theorem, we call such P is the characteristic of D. And so P characteristic of D, or D has the characteristic P. If P is the least integer that satisfies P times 1 is equal to 0. Let's see a few examples. Obviously, the set of integers, rational numbers, real numbers, and complex numbers have infinite characteristic. And for prime P has characteristic P. Or prime characteristic. And another example is a little interesting example. Suppose F is a field of characteristic 2. And in this field, addition and subtraction are the same. Okay, so it sounds confusing, but so since the characteristic is 2, so for every element of F, we have 2a is equal to 0. But this means a plus a is equal to 0. But this means a is equal to negative a, right? So that means b plus a is equal to b minus a, because a is equal to minus a. So addition and subtraction are the same. Now consider this field E, consisting of 0, 1, alpha, beta. So there are 4 elements, but its characteristic is P. Okay, as you can see, 1 plus 1 is 0. So it has prime characteristic, which is 2. Characteristic is 2. And so that means even if if a field is finite, then its characteristic must be finite. But it doesn't mean the number of elements of the finite group is equal to the characteristic of that field. Okay, and you should also note from these tables that this subset F 0 and 1, it's a subfield of E. Okay, so this means if we pick only these parts, then it is closed under addition and multiplication and satisfy all the axioms of a field. So we can say F is a subfield of E. Okay. And we will define subfields more precisely later. And consider this polynomial x squared plus x plus 1. This does not factorize in f of does not factorize in as a polynomial of x over f, but it does in E as a polynomial of x over a, because this is equal to x squared and 1 is equal to alpha plus beta. Okay, alpha plus beta is 1. So this is equal to alpha plus beta x. And 1 is also equal to alpha times beta. So this is alpha beta, and this can be factorized as this. And we also note that, let's see, this part of the multiplication table makes a closed group. It's a group. It's actually a cyclic group. So E except for 0 is 1 alpha beta, and it is a cyclic group. In fact, alpha times alpha is beta, and beta times alpha is 1. So that means alpha cubed is equal to alpha squared times beta, which is alpha squared times alpha, which is beta times alpha, which is equal to 1. So this is actually equal to 1 alpha and alpha squared. So it's a cyclic group of order 3. And we can also see that this is also equal to 1 beta and beta squared, because beta times beta is alpha and alpha times beta is 1. So this is a cyclic group generated either by alpha or beta. Now let us define subfields more precisely. Let E be a field and F be a non-empty subset of E, and then we say F is a subfield. It's just like subgroup or subring. We can define subfield of E if F is a field with the same addition and multiplication as E. Okay, so it's closed under addition and multiplication that are the same operations as in E, and satisfies all the axioms of a field. And just like we had subring criterion or subgroup criterion, we can also derive subfield criterion. So subfield criterion. And again, suppose E is a field and F is a non-empty subset of E. then E is a field if and only if the following are satisfied. One, A, F is closed under addition. And 1B, for all A in F, we have negative A is in F. So additive inverse is also in F. And second, so these are about addition, and about multiplication. 2A, F is closed under multiplication. And B, the element 1 is in F. So this one is the identity element of E, of course. And C, for all A in F, and A is non-zero, then A inverse is also in F. Okay. So this subfield criterion says we don't need to check all the axioms of a field to see if a subset of a field is a subfield. Okay, we only need to check all these 5 points. Okay, so this is if and only if, so we need to prove both directions. But if E is a field, of course these are satisfied. So the only if part is trivial. And the if part. So if these are satisfied, then that means F is a subring. F is a subring of E by subring criterion. And all the other axioms of a field of the field are satisfied by F because they are also satisfied in E. And you should check all of these. But like commutativity of multiplication and the existence of identity is already satisfied, and the absence of proper divisors of 0 are of course satisfied because it's satisfied in E. Is that it? So all the inverses are there. So yeah, so it's done. That's it. Okay, let's see an example. That is this set of real numbers, a plus b square root of 2, where a and b are rational numbers, so this is a subset of real numbers. And we want to show that this is a subfield of real numbers. Okay, of course this is not empty, so that's okay. And so let's check all the subfield criterion. So first we need to show that it's closed under addition. So suppose a, b, c, d are rational numbers. Then a plus b square root of 2 plus c plus d square root of 2 is equal to a plus c and b plus d square root of 2. And a plus c is a rational number. B plus d is also a rational number. So this is an element of F. So this is okay. not 2, but b. So a plus b square root of 2 is in f, and negative a plus b square root of 2. So this is obviously the inverse element of this number in this set, okay? But we need to show that this is also in f. And so maybe we should write this as plus negative b square root of 2. And negative a is a rational, and negative b is also rational, so this is an element of f. Therefore, the additive inverse of a plus b squared of 2 is in f. So it's okay. Next, about multiplication. We also assume this. Okay, so let's multiply these two elements. And that will be AC and BD, 2BD, because of square root of 2's, plus, and let's see, AD plus BC, square root of 2, which is in F. You know, all these are, both of these numbers are rationals, so this is an element. So it's closed under multiplication. And B, what was it? Let's see. So element 1 is in F. Yeah, it is. So 1 is 1 plus 0 times square root of 2, which is an element of F. So this is fine. And C, the inverse of, okay, so A plus B square root of 2. If this is not 0, okay, then we should have a multiplicative inverse of this element. Okay, so this means so if this is not 0, then either A or B is not 0. Okay, so let's see. In real numbers, the multiplicative inverse of this is just 1 over this, right? So since we're assuming it's non-zero, this is fine. But this is not in the form of something plus something times square root of 2. So we need to modify this a little bit. So let's try multiply both numerator and denominator by a minus b square root of 2. So a minus b square root of 2 and a plus b square root of 2, a minus b square root of 2. And this is equal to and a squared and minus, let's see, minus 2b squared. Okay, but is this okay? Let's see. So we are assuming this is not 0. Does this imply a squared minus 2b squared is not 0? Let's see. Yeah, looks like it. So this means a is not equal to negative b square root of 2. So if we multiply both sides, square both sides, then a squared is not equal to 2b squared. Therefore, this is non-zero. Okay, so that's fine. So this is okay. So a and a squared 2b squared plus negative b a squared minus 2b squared square root of 2. So this is a rational number, and this is a rational number, times square root of 2. So this is indeed an element of F. So this subset of real numbers satisfies all the points of the subfield criterions. Therefore, F is a subfield of real numbers.